Hello everyone, I am Runal Dhaude, an electronics and telecommunications student currently interning at Emertxe Technologies. And during the tenure of my internship, I had the opportunity to work on an exciting embedded system project, a fully functional microwave oven. Through this presentation, I will take you on a journey through the technical foundation, implementation, and working of the project. From understanding the role of the microcontroller used in this project to how embedded C programming brings system to life, I will walk you through the key aspect that makes this microwave oven project both efficient and reliable. Also, this project was conducted under the guidance of a mentor, Jayalakshmi ma'am. Before diving into the project implementation, I would like to discuss the learning outcomes from the internship classes conducted. The entire internship program was conducted in two phases, the training phase and the project implementation phase. In the training phase of the internship, a C language foundation was built, which was the basic requirement for the project. In this, the basics of C language, such as what are the different data types involved, what are the basic input and output functions which are used to display the messages or to take inputs from the users, which are the printf and scanf functions, were taught and discussed. What are the different control structures, the if-else statements, switch case statements, the different loops such as for loop, while loop, and do while loops were discussed. What are the different operators like the arithmetic operator, logical operator, assignment, relational, and bitwise operators, where and how to use those was all taught and discussed. Along with this, the advanced concepts such as ternary operators, what is the concept of overflow and underflow, what is array, what is a pointer, how to return an array, how to handle the null and while pointers, how to pass a variable by reference or by value, how is memory allocated to different variables depending upon the data type, what is a static variable in C, what are recursive functions, what are the constants used in C, and the other keywords. Along with all this, the advanced concepts such as strings, storage classes, preprocessor, and macros were discussed and taught in the first week of the training phase. In the week 2 training, the microcontroller module was involved, in which the introduction to embedded systems was done. What exactly is an embedded system? What is its definition? And the examples in our daily life what of embedded systems were discussed. What are the different categories of embedded systems? The ones discussed were the standalone embedded system, real-time embedded system, networked and mobile embedded systems. What are the different components that are integrated seamlessly to form a complete embedded systems? Those components studied were sensors, ADCs, actuators, microcontrollers, digital to analog converters. What are their roles and functions in an embedded system? Everything was discussed in detail. Along with this, the study of microcontrollers and microprocessors, the different microcontroller architectures. The ones discussed were the Van Neumann and the Harvard architecture. The comparison between the microcontroller and microprocessor was discussed. What are the different types of memories that are used in these controllers and processors? The ones discussed were the RAM, ROM, hybrid memories, the NAND and NOR memories, and the different categories of these primary memories. Along with it, what is SoC, that is software on chip, the information about it was explained and taught in detail. Basically, the training phase was to build a foundation about C language and the microcontrollers, which was the major necessity in order to build the micro oven project. Now let us examine the implementation structure of the project as how and what things are involved in it. In order to build a micro oven, the hosting platform is the MPLab IDE version 5.35 functioning on the user's laptop, that is my personal laptop, and the target is achieved using the PiximLab simulator, which will display and verify the outcomes of the code. And the cross compiler used is the XC8 cross compiler, which is a software tool that will generate the code that is executable for different computer platforms than it's running on. To be precise, it translates the code to run on a target architecture that is not same as the host architecture. In this case, the host architecture will that be of the MPLab, and the target architecture will be that of the PiximLab simulator. Now, as mentioned before, the categories of embedded system, the micro oven project is a standalone project. Now, what is a standalone project? A standalone project is a project which simply follows the instruction and doesn't involve any feedback. It is capable of taking decision on its own by simply following the instructions given by the coder. A daily life example other than the micro oven for the standalone project will be a semi-automatic washing machine. Moving ahead, the simulation board used is the PIC Genius board and the microcontroller is the PIC16F877A. Along with this, the various peripherals integrated to complete the project are the CLCD, timers, matrix keypad, buzzer, fans and switches. Before going towards the peripherals, let me discuss the major and important component used in the micro-oven project, which is the PIC16F877A microcontroller. PIC16F877A is an 8-bit microcontroller that follows the Harvard architecture. This microcontroller is widely used in embedded systems due to its versatility and ease of programming. It comes with a 368 bytes of RAM and 14 KB of flash program memory, which is used for storing program code. This allows it to handle small and medium sized embedded applications efficiently. This microcontroller has a total of 5 ports, namely ports A, B, C, D, and E, which provides 33 input-output pins for interfacing with external devices. These ports allows it to communicate with sensors, displays, motors, and other peripherals. It requires an external crystal oscillator of up to 20 MHz for operation, ensuring stable clock timing for processing tasks. The PIC16F877A also supports several built-in peripherals such as analog to digital converters, which are used for sensor data processing, the pulse width modulation PWM for motor control, the timers for precise time-based operations, the serial communication protocols for data exchange. Also, it can interface with various devices including the LEDs, switches, LCDs, buzzers, and fans, making it a suitable choice for automation and controller applications. It also supports universal asynchronous receiver and transmitters, the SPIs, and I2C protocols, allowing it to communicate with other microcontrollers, memory modules, and external devices efficiently. Overall, the PIC16F877A is a powerful and flexible microcontroller, ideal for applications requiring multiple peripheral interfaces, serial communication, and efficient processing in embedded systems. Moving towards the peripherals involved in the microwave oven project, the first peripheral that we'll be discussing is the CLCD. The character liquid crystal display is an important peripheral used in a microwave oven project. This display is commonly used for alphanumeric outputs, making it ideal for embedded applications where text-based information needs to be shown. The CLCD used is controlled by the HD44780 driver, which simplifies the communication between the microcontroller and the display. It supports both 4-bit and 8-bit modes, allowing flexibility in data transfer. The display is capable of showing letters, numbers, and symbols, making it useful for providing status updates or user instructions in embedded systems. Further, taking a look at the pin configurations, the CLCD module has 16 pins categorized into the power pins, which are the VCC plus 5V pin, pin number 1, which provides power supply to the display, the ground pin or pin number 2, which connects the CLCD to the ground. Further, we have the control pins, which are the RS or the register select pin, which is used to determine the type of data being sent. If this pin is 0, it indicates the command mode and which is used for sending instructions like clearing the screen, etc. And when the RS pin is enabled, it is used as a data mode for displaying characters on the CLCD. We have another control pin, which is the R/W, or more precisely R/W or read write pin. When this pin is enabled, it is used as a read mode to read data from the CLCD, and when it is off, it is used as a write mode to send data to the CLCD. Another pin we have is the enable pin. When the enable pin is enabled or when it is 1, it triggers a data transfer. Further, the data pins of the CLCD starts from D0 to D7 for 8-bit mode and D4 to D7 for 4-bit mode. The 4-bit mode saves the microcontroller pins by transferring data in 2 steps. Also, I would like to discuss along with all this the methods used to check whether the CLCD is busy or not before sending any data or instruction to it. Those two methods are the poll for busy flag method and the delay method. In the poll for busy flag method, from the microcontroller to CLCD, we'll send some data using the D0 to D7 pins. It will start processing the data, and if it is busy, the CLCD will set the D7 bit to 1 to indicate that it is busy. Whereas in the delay method, we provide the delay which we get to know from the CLCD data sheet, which is taken by the CLCD after every instruction. It is an easy method as compared to the poll for busy method. In this way, we check whether the CLCD is busy or not before transferring any instruction or data to it. Overall, the CLCD is an essential part of our project as it provides a clear and simple way to display information. By using proper pin configuration and modes, we can efficiently control the display and integrate it with the micro oven system. Going towards the next component, that is the tactile switches. The tactile switches are momentary push button switches that provide a physical click sound as feedback when pressed. These are commonly found in the mouse buttons or the mobile phone's volume buttons and other compact input devices. Due to their simple operation, they are widely used in embedded systems where limited user input is required. The tactile switches can be interfaced with the microcontroller using either a pull up or pull down configuration. Discussing about the pull up and pull down configurations. In the pull up configuration, when the switch is pressed, the microcontroller pin is connected to the ground, that is logic 0, and when the switch is released, the pin is connected to VDD, that is logic 1, via the pull up resistor. Whereas in pull down configuration, when the switch is pressed, the microcontroller pin is connected to VDD, that is logic 1, and when the switch is released, the pin is connected to ground, logic 0, via the pull down resistor. These configurations can be triggered via either level triggering or edge triggering. A common issue that arises with the edge triggering is the bouncing effect, where the switch may resist multiple presses due to mechanical vibrations. This is solved using a software delay, basically a for loop delay or hardware debound circuits to ensure a stable signal. This was all about the overview of the tactile switches, and now we'll see how these tactile switches together form a matrix keypad. Now taking a look at the next peripheral, that is the matrix keypad. A matrix keypad is commonly available in 4x3 or a 4x4 configuration and is widely used as an input device in embedded systems. The one which we are using for a microwave oven project is a 4x3 configuration matrix keypad, and it consists of tactile switches arranged in a row column matrix, making it efficient for detecting multiple key presses with fewer microcontroller pins. The keypad operates by scanning the rows and columns to detect which key is pressed, and each key press connects a specific row to a column, allowing the microcontroller to identify the pressed key. The rows are configured as outputs and are driven high-low sequentially during scanning. The columns are set as inputs to detect the key presses. The microcontroller scans the rows and then one by one while checking which column is pulled low, indicating a key press. A software function is implemented to read the key press, detect edge or level triggering, and store the key in a variable for processing. This method ensures accurate and reliable key detection. The matrix keypads are a simple yet effective way to provide user input in embedded applications. The row column scanning mechanism helps to minimize the number of required microcontroller pins while maintaining the efficient key detection. This is all about the matrix keypad that we have integrated in our project. Moving ahead to the next important peripheral, which is the timer. Now, timers are counters used in embedded systems to measure time intervals or generate precise delays. They can operate using either an internal clock or may require an external clock source. The basic functions of timers is basically delay generation, which is used for time sensitive operations like setting time delays, event counting, which tracks external pulses to count events, and interrupt triggering, which generate interrupts at specific time intervals for periodic tasks. And the timers we'll be discussing will be that of the PIC16F877A microcontroller, as it is the concerned microcontroller for our microwave oven project. So the PIC16F877A microcontroller has three timers, which are the timer 0, which is an 8-bit timer, and it uses a prescaler to adjust clock speed and can function in timer/counter mode. Now speaking about the prescaler, what exactly is prescaler is? A prescaler is a divider that reduces the clock frequency before feeding it into a timer. This allows the timer to count at a slower rate, extending the time interval before it overflows. Next we have the timer 1, which is of 16-bit, and it supports longer time delays and can work with an external clock. Further we have the timer 2, which is an 8-bit timer. It is used for PWM, that is pulse width modulation generation, and includes postscaler and prescaler for frequency control. Now as I have told about the prescaler, what is postscaler? A postscaler is used after a timer overflows to further divide the output frequency. It basically controls how often an interrupt is generated from a timer overflow. Also, the timer used for our oven project is the timer 2 of the PIC16F. Further, moving towards a watchdog timer. The watchdog timer ensures the system reliability by setting the microcontroller if it hangs or encounters a malfunction. Basically, the watchdog timer is a timer which keeps a watch on the functions of the microcontroller. Now next we have in timers a concept known as interrupt service routine or ISR, which is a special function that runs automatically when an interrupt occurs. The processor pauses its current task, executes the interrupt service routine, and then resumes its normal operation. In timers, an ISR is triggered when the timer overflows, allowing scheduled execution of the tasks. Overall, the timer plays a crucial role in embedded systems by managing the timing operations, even counting and interrupt handling. They help maintain accuracy and efficiency in the microcontroller based applications. So, timers are a very important and integral part of our microwave oven project, without which the project won't be carried out smoothly as it should go. Now, let us take a look at the code for the microwave oven, which was implemented as a part of this project, followed by a simulation of the microwave oven. The code for the microwave oven system has been implemented by integrating the various code modules of the various peripherals used, which are the CLCD, timers, matrix keypad, and so. How does the code works? The code initializes the CLCD display, sets up the matrix keypad user input, configures the fan and buzzer pins as output, and initializes the timer too, and enables the peripheral and global interrupts. Also, it contains the main loop, which is the while one loop which runs infinitely and which continuously reads the keypad input, and the system operates based on different states using a finite state machine. The program follows different states represented by operational flag, which determines what the microwave should do. The different screens implemented for the microwave oven are the power on screen, menu screen, and the modes include the micro mode, grill mode, convection mode, and the functions that are mentioned over here are the display time function, the pause and stop functions of the microwave oven. Depending upon the key press, the microwave oven switches to the particular mode or the particular screen. In the switch statement, uh, the functions for the particular screens and the modes have been mentioned, whereas the definitions of these functions is mentioned in the microoven.c file. The main.c file is the main file of this project, which includes all the features and how and what the micro oven should do, and the definitions of the functions involved in the main file are defined in the microoven.c file. Basically, the main.c file contains the code which allows the user to select the cooking modes and set time and temperature, perform starting, pause, and stopping the oven operations. Further, taking a look at the function definitions mentioned in the microoven.c file. In the microoven.c file, various functions are defined, such as the power on screen function, clear screen function, display menu screen, set time, and the time display function has been mentioned along with the set temperature function. These all functions, the logic for these functions are implemented in this file, and these have been called in the main.c file. Taking a look at the main.h file, the main.h file contains all the necessary macros that are required for the main.c file. Whereas the microoven.h file involves all the function prototypes of the functions defined in the microoven.c file. The peripheral modules are used by integrating their .h files in the header files of the main.c file as well as the microoven.c file. And all this integration together builds a complete micro oven system. Now let's take a look at the simulation of the microwave oven project. As mentioned earlier, the board is the PIC Genius board and the microcontroller is the PIC16F, and which operates on a clock frequency of 20 MHz and 16:4 CLCD displays used. Let us start by loading the hex file of the project, which is the microoven.x file. First, the power on screen is implemented, and then the menu screen. And the menu screen has 4 options, out of which we'll go for the micro mode. We'll set the time. This is the display time screen, and accordingly we'll use hash to accept the entered value. The key press of 5 is used to pause the time, 4 is used to resume the time, and 6 is used to move out of the mode. So once we pause and start, and if we want to exit, we can press 6. The next mode is the grill mode. Again, the time display time screen is implemented in this mode. Hash is used to accept the values entered, and clear is used to clear the values. The same functionalities, 4 is pressed for starting or resuming, 5 is pressed for pausing, and 6 to come out of the mode. Next is the convection mode, which allows us to set the temperature. We set the temperature using the keypad, and here we have implemented a preheating screen that takes 1 minute of time to preheat the oven. Once this screen is once this timing is completed, the time of 1 minute, we are able to set the time. It may take a while, as it completely takes 1 minute in order to shift the screens. Once the preheating time is complete, we are allowed to set the time, and we set the required time. And again the same thing, the screen is implemented, where the 4 is used for starting, 5 is for pausing, and 6 for coming out of the mode. And same goes with the start mode. The start mode, the 4 is used for starting and resuming, as well as once the time is paused and when again it is resumed, the time is added by 30 seconds. And the 6 is again implemented to come out of the mode. Also, the alert message that is displayed once the cooking is complete, I'll just show you a demo. Once this time is completed, once the cooking is done, the message that we get over here is the time up, enjoy your meal message. And with this, the implementation of the microwave oven completes. Last but not least, I would like to thank Emertxe for providing me this opportunity, and our mentor Jayalakshmi ma'am for constantly guiding us through this internship and this project. I'm very grateful for the opportunity that I got, and thank you so much everyone.